Now I am. Sorry.
Can you do C as well, please? Thank
All
you.
right, well, let me just stop for 1 second. Well, okay, I'll do C and then I'll come back. C. C is the congruence 8x congruent to 15 mod 26. So the greatest common divisor of 18 and 26, that's my number D, is 2. And 15 is not congruent to 0 mod 2. So there is no solution. This congruence has no solution. And 14D, let me just finish the problem, is 14x congruent to 21 mod 17. So D, which is the greatest common divisor of 14 and 17, is 1. So 21, and every number is divisible by 1. So this congruence has a unique solution modulo 17. And you could do it, you could find the solution again by trial and error. An alternative way is to solve using the Euclidean algorithm. So the Euclidean algorithm will express 17 and 14, will express 1 as a linear combination of 17 and 14. How does it do that? 17 is 14 times 1 and a remainder of 3. 14 is 3 times 4 and a remainder of 2. 3 is 2 times 1 and a remainder of 1. So we can write 1 is 3 minus 2, but 2 is 14 minus 3 times 4. So this is 3 times 5 minus 14 times 1. But 3 is 17 minus 14 times 5 minus 14 times 1. So this is 17 times 5 minus 6 times 14. So we have this expression, 1 is the following linear combination of 14 and 17. This is 5 times 17 minus 6 times 14. We want 21. 21 is then 21 times 5 times 17 minus 21 times 6 times 14. So this is 21 times 5 is 105 times 17 minus 126 times 14. So another way of saying that is that, oops, okay, I think I did something that's not quite right here. What's going on? Well, so this says that 14 times minus 126 is congruent to 21 mod 17. So the solution is, this is not the best way to write it, x congruent to minus 126 mod 17. I want the least non-negative residue. What is 126 when you divide it by 17? This goes in maybe 7 times. 7 times 7, 119. So if this is correct, 126 is 7 times 17.
Professor, on the last line where you wrote equals 17.5 minus 6, 17
No,
times
17,
5
it's 17 times 5. Yeah.
minus 6 times 14. Where did you get the 6 from?
I have 17 times 5. Here I have 5 times 14 and 1 times 14. That's 6 times 14.
Oh, got it. Thank you. Sorry.
So minus 126 is, let me write this as, so this is minus 7 times 17 minus 7. If I add 17 to this, I get minus minus 8 times 17 plus 10. So let me just check if this is correct. 8 sevens are 56, minus 136. So this is correct. So this is the same as 10 mod 17. And let me just check if this is correct. So 140 times 10, 14 times 10 is 140. If I divide 17 into 140, this goes 8 times. 8 sevens are 56. These are a remainder of 4. 21 is the same as 4 mod 17. I could have made that reduction in the beginning, though it didn't matter. So this is correct. So there's a little bit of arithmetic you have to do, but this congruence, the one we started out with, has a unique solution mod 17. It's all integers congruent to 10 mod 17. Yeah. Okay. That's the answer. Other questions I might do?
Just one request. Can you please either post the video of or the sheets for problem session 5-2?
If I can, yes, I will try. I've been having a lot of trouble uploading to YouTube, but I will keep trying.
I understand. That's just 5-2. It's the only one that's missing. Thank you.
Okay.
Professor, would you mind doing question 12 from the review?
I'm sorry, which one?
Question 12 from the review.
Okay. So m is a positive integer, and we have a congruent to b mod m. So let D be a common divisor of A, B, and M. So that means I can write A as D times A prime, B as D times B prime, and M as D times M prime. Now, A congruent to B mod M means A minus B is some multiple of M. It's M times Q for some Q. Now, just replacing A, B, and M by these expressions, I have dA prime minus dB prime is dM prime Q. And I can divide by D, A prime minus B prime equals M prime Q, which means A prime is congruent to B prime mod M prime, but A prime is just A over D, B prime is B over D, and M prime is M over D. End of proof.
Could you go over the proof for Theorem 9, please?
Okay. Theorem 9 on the review sheet. Okay.
Yes, yes.
All right. So Theorem 9 says that congruence is an equivalence relation. So the first part is to prove the relation of congruence modulo M is an equivalence relation. So first of all, for any number x, x is congruent to itself mod M, because x minus x is 0, which is divisible by M. It's M times 0. So this proves the relation is reflexive. How do we prove it's symmetric? Well, if x is congruent to y mod M, that means x minus y is a multiple of M multiplied by minus 1. Y minus x is minus MQ, which is M times minus Q, which means y is congruent to x mod M. So that's the proof that it's symmetric. How do we prove it's transitive? Well, if x is congruent to y mod M and y is congruent to z mod M, this means that x minus y is a multiple of M. This means that y minus z is some other multiple of M. Suppose we add the equations. The y's cancel, we get x minus z is mq plus mt, which is m times q plus t. So x minus z is divisible by m, so x is congruent to z mod m. So that's the proof that it's transitive. An equivalence relation is a relation that is reflexive, symmetric, and transitive, so this works. So that's the first part of the theorem. Are there any questions about that? Okay. What about the second part? Let a be any integer by the division algorithm. We can write a, if you divide it by m, it's m cubed plus r, and the remainder r is an integer between 0 and m minus 1, which means a is congruent to r mod m. So that means that every integer is congruent mod m to some number between 0 and m minus 1. And I want to show it's unique. So suppose r and s are in this set, and that a is congruent to r mod m, and a is also congruent to s mod m. So by the fact that that this is an equivalence relation, r is congruent to s mod m, which means m divides the number r minus s. Particularly, it divides the absolute value. But r and s are between 0 and m. So the furthest apart any two numbers in this set can be is m minus 1. So if a number less than or equal to m minus 1 in absolute value is divisible by m, it only can happen if r minus s is 0, so r equals s. So this is a proof of the uniqueness. Every number, every integer modulo m is congruent to one and only one of the numbers in this set.
Can you explain the part where you said by the division algorithm, a is equal to m cubed plus n? Can you, I'm not sure what you mean by that.
Okay. So just 1 second. So the division algorithm is the very first thing we did, and it's what you learned in elementary school. It's long division. So the division algorithm is simply the following statement. Let d be a positive integer. Every integer n can be written uniquely in the form n equals dq plus r, where q is the quotient, r is the remainder, and what uniqueness means is when you divide by d, the remainder is an integer between 0 and d minus 1. That's all. That's the division algorithm.
Yeah, thank you. Yeah, thank you.
Okay.
I don't know. Does that, because it says that every integer is congruent mod m to exactly one element in the set from 0 to m minus 1, but wouldn't every number be congruent to 0?
No, not at all. So suppose I
Mod
take
M.
m equals 7, and I take the number n equal 23. So 23 is 7 times 3 plus 2. So 23 is congruent to 2 mod 7. Because 23
Sorry,
minus 2.
I was thinking about it backwards. Makes sense. Thank you.
Yep.
Can you put the last piece of paper back on the screen really quickly? Sorry. In the last line where you say m divides n minus s, and then n minus s.
R minus s. This is an R.
R, sorry. So you say m divides r minus s, and that's less than or equal to m minus 1. Why does that imply that n minus s, or excuse me, r minus s is equal to 0?
Okay, so let me just continue it down here. So we have a number a, which is congruent to r mod m, and a is also congruent to s mod m, and r and s are both integers between 0 and m minus 1. Okay, now r is congruent to a is congruent to s, so r is congruent to s mod m, which means m divides the difference. Right? That's the definition of congruence. R is congruent to s means r minus s is divisible by m. And similarly, s minus r is. So m divides whatever is the absolute value. Now, here's the number line from 0 to m minus 1. R and s are two numbers between 0 and m minus 1. The furthest apart they can be is m minus 1. So we have that on the one hand, r minus s is some multiple of m, but it's equal to or less than m minus 1 and greater than or equal to 0. Well, a multiple of m is like 0m, 2m. The only multiple of m which is less than or equal to m minus 1 is when q is 0. It is. If r minus s is divisible by m, r has to equal s, because otherwise they would be at least m apart.
Okay, thank you so much. That makes sense.
Okay. Other problems we can do? Okay. All right. Well, if there's nothing else, we'll stop. The only thing I will do is I just found the notes from problem session 5.2. So what I will do is the following. I'll just photograph them right now. I'll put them in this problem session right now. So,
Excellent. Thank you.
so just for the record, I had recorded after I finished the first page of this problem session. So this was problem session 7.1, and I calculated the Euler phi function. And there it is for the record. In problem session 5.2, I have just 3 pages of notes. So this is the first page. This is the second page. And this is the third page. Okay.
Thank you.
Sure. So if there are no more questions, we will quit now, and I will be back online this afternoon at 4 o'clock. Okay. Bye, everybody.
Thank you.